Okay, let's get started. I guess this is part nine. This is going to be probably the shortest stream we'll ever do because yeah, we've pretty much built the entire model, and I'm just going to walk through the final uh, transformer implementation, the whole thing. We'll just take a look at a couple of the details and then also talk about what's next. So I've been looking at things like how you know things work under the hood in Candle, specifically when we talk about launching GPU kernels, in this case, Apple's Metal framework being used to launch those kernels. And then there's also uh, the idea that, the backpropagation implementation itself in Candle, how does that look like? Obviously, you're going to have to build what's called the computation graph, and then use that in the backward pass. So pretty much every tensor that uh, you use or you create as you build your model, you want to have operations attached to it so that you can build the graphs. We'll look at that maybe later. But to quickly get started, so here's our implementation. Pretty much all of these layers are done. Let's look at the transformer, the full transformer. So this is the full transformer. Let me just minimize that. Well, it's actually pretty simple. So if you take a look at the full transformer, okay, where's that? Sorry. Yep, that's where we are. So if you take a look at the full transformer, we've got the encoder and we've got the decoder. In the encoder, we've got these blocks. In the decoder, we've got similar blocks, just one additional, a couple of them repeated and slightly modified. You've got masked multi-head attention. You don't have it over here. So let's just look at that. If you see how this works over here, you should be, you should be able to pretty much intuitively see that you can map that entire architecture into, code. So the simplest way we do that is let's just have a transformer with all of the building blocks. That means your input embeddings for your encoder, for your decoder. Again, for your encoder, you have positional embeddings. Again, for your decoder, you have positional embeddings. And then uh, you've got a projection layer, all of that stuff. And then you go ahead and uh, implement your encode and decode functions. We've already seen this before, so I'm not going to jump into it. But initially, what I want to focus on is how do we actually build the transformer, right? So you pretty much want to put all these blocks together. So here's what I'm going to do. I'm going to say, okay, these are my source input embeddings. We'll also have something called target input embeddings because we're actually working on building a translation, you know, model, which is going to translate an input to an output. The source language could be something else. The target language could be something else. We've not figured out what languages we're targeting, but we'll figure that out later. And then the same thing for positional encoding. Then you go ahead and create your encoder blocks, which is, this one's going to be 6 according to the paper, so we'll use that. We go ahead and create our decoder blocks again. So, and then we have a full encoder and decoder. That means we've got the sequence of blocks, and that's our transformer, right? So we have the entire state that we need to actually move forward, to give it some input, and it should be able to produce something, and the forward pass. And the forward pass is just one part, all right? You also have the backward pass, and then you've got the updating the weights phase or the optimizing phase. So we've done with the forward pass. We'll get to the backward pass, but in order to get to the backward pass, you need to understand something called the backpropagation, which is like the foundational algorithm that works up here in training the model and basically building a set of weights that will be able to do the translation, right? So yeah, I don't think there's a lot to talk about because these are all uh, just blocks that are composed, and finally in one single, finally uh, we're able to implement the full transformer architecture in just one single file. So we'll be using this as we go along to figure things out. As a sneak peek for the next part, I've also been working on how does metal actually work under the hood in dispatching metal kernels. Obviously, there's a lot of use of Rust types, etc. Most important ones are what's called storage and tensor, and it's interestingly done. I think it's sort of efficient. I still need to get a hang of things so that I understand a couple of things. But I also noticed that the one nice thing is they're using metal flash retention, which is this particular, uh, what is that? Yeah, which is this particular implementation. It's open source. It's an actual alternative to Apple's own metal performance shaders, or MPS. These are just basically kernels that you deploy on the GPU to do the work. Somebody actually wrote an open source one, of course, in Swift. So what the Candle folks did is they just took the compiled artifact and started using it in Candle. Makes a lot of sense, right? So yeah, that's where we are. The full transformer is now available. I mean, if anybody's watching this, you could probably just take a look at this and see if they find anything wrong with it. Let me know. That'd be great. All right. Thank you. And yeah, catch you next time.